In this section, we're going to learn about the central limit theorem. It's probably one of the most foundational theorems in statistics that allows us to make inferences from the sample to the population. We can basically predict things about the population with a little more accuracy. It helps us establish a relationship between a sample and the population, or how big of a sample. So to better understand the relationships between samples and populations, what I recommended that we do is we start with a really small population. Again, if we only had 4 in our population, we would never do a sample because it's just too small, but we're trying to look at the relationship between a sample and its population. So the easiest way to do that is start with a very small population and consider samples of it. So in this example, we're looking at 4 student shoe sizes. One student has an 8, a 9, 11, and 12, so it's somewhat uniform distribution. If we had with somebody with a size 10 shoe here, it would have been a perfectly uniform distribution where there's one of each. So now what we're going to do is from this population, first let's understand in the population we could kind of cheat and we could find the population mean, which again, the goal of a sample is to find the mean of the sample as a point estimate of what it would be for the population. But since the population here is so small, we can just calculate the mean. We can just add these together. If you add those together, that's 9 plus 11 right there in the middle is 20. 8 plus 12 is 20, so that's 40. These sum to 40 divided by 4 is 10. So the population mean of that data set, I already know the answer is 10. That's what I'm going to try to see which samples work out the best. We could also do this now by looking at, let's look at every possible sample of size 2 with replacement. What that means is I'm randomly going to pick one of these numbers, like let's say I randomly pick the 8. And put that down in my sample, and then I put it back, and then I randomly pick another number, and I could potentially pick the 8 again, so that's sampling with replacement. So sometimes you'll pick this up. So this represents, this chart here, every possible sample of size 2 from that population. So in this example right here, one potential sample is 8, 8, and the sample mean of 8 and 8, if that's the sample, would be easy enough. That would be 8, because 8 plus 8 is 16, and 16 divided by 2 is 8. All right, another potential sample with replacement for that population, if I grab 2 of them, could be 8 and 9. 8 and 9 is another potential sample, and if you average those two, that would be 8.5. Again, if you want to, you can add those together. That's 17. 17 divided by 2 is 8.5. Another potential sample is 8 and 11, and if I add those two together, 8 plus 11 is 19, and 19 divided by 2 is 9.5. Another potential sample would be 8 and 12. So if I add those together, which would be 20, and 20 divided by 2 is 10, which that one hit perfect. So if you had 8 and 12 as your sample, it perfectly described the mean of the population. We're pretending like we don't know the population mean is 10. We're seeing which one of these samples would give us good estimates. All right, let's try another sample. We could potentially have the sample 9 and 8. If you flip it around, you pick 9 the first time, then put 9 back and pick 8 the second time. So 9 plus 8 divided by 2, that would be 8.5 again. It is possible with replacement we could get 2 9s. I accidentally randomly pick a number here and I get 9, put it back, and I randomly pick another number and I get 9 again. So that would be, the average of 9 and 9 is 9, obviously. Then we could have 9, 11, that's another sample. So 9 plus 11, that's 20. 20 divided by 2 is 10. 9 plus 12 is 21. Divided by 2 would be 10.5. 11 and 8 is another potential sample of size 2. So 11 plus 8, that's 19, and 19 divided by 2 is 9.5. 11 and 9 go in the other direction. That would be 20. If I add those together, divided by 2 would be 10. 11 and 11, the sample of that, or the sample mean would just be 11. 11 plus 11 is 22. 22 divided by 2 is 11. 11 plus 12 is 23, and 23 divided by 2 is 11.5. 12 and 8, another potential sample. And you can see I kind of methodically did this. I did all the where the 8s came first and the other numbers. Then I did all where the 9s came first and all the other numbers. Then I did all the 11s and where the other numbers. Now I'm putting 12 first and then all the other numbers. So you can see I systematically went through and created every possible sample. 12 plus 8 is 20. 20 divided by 2 is 10. Next one's 12 plus 9 is 21. And 21 divided by 2 is 10.5. And then the next one, 12 and 11, if I add those together, that's 23, and 23 divided by 2 is 11.5. And finally, the sample mean of 12 and 12 would be 24 divided by 2, which is 12. So what I just done, I've represented every possible sample mean of size 2 from that population. And now we're going to make a frequency distribution of this and kind of see which answers are good and which answers are bad. So a frequency histogram basically means I'm going to put that data in there and create a histogram. Just remember that basically if you hit the number exactly in the middle, so if I hit 8.5, it goes to the right, and you can see I used a square bracket to describe that. So let's go through and place each one of these in the right place. So 8 would perfectly fit right here. 8.5 would fit right here, because anytime you land right on the line where it moves over, you move to the right, so that's 8.5. 9.5, that would be right here. I'm just putting the numbers in each one. 10 would be next, that would be right here. 8.5, just going through and doing each one. 9 would fit right there. 10, right here. 10.5 would be to the right. 9.5, let's see if I can find 9.5, that would be right here. 10, right there, and then 11, be right there. I'm just trying to block all these in 11.5, that would fit all the way on the end over here. And then after that we have 10, which is right there in the middle, and then 10.5, that would be a little bit to the right. 11.5 is next, which would be right here, and finally 12. So here's the histogram. So we have 3 data points in this range, and I want you to notice something. The original population distribution was completely uniform, and the distribution of the sample means is somewhat normal, and that's a huge part of the central limit theorem. That's really what the most important part of it. It basically suggests that regardless of the population, the distribution of the sample means, the larger the sample, the closer it gets to becoming a normal curve. You can see right here where I just did those points, I just did samples of size 2, I got a pretty close to a normal curve. If I just knocked 2 more of these off, that would be as symmetric as possible, but still very close. It says find the percentage of the 16 means from problem number 3 that are at most, really that shouldn't say problem number 3, that should just say the chart, at most 1 unit from the mean, i.e. they're somewhere from 9 to 11. This would represent the percentage of times the random representative sample of size 2 would be within 1 unit of our correct mean. So we know the answer is supposed to be 10, and they're asking which ones are good predictions and which ones are bad predictions. And we're suggesting anything from 9 to 11 is a good prediction. Alright, so that would be a good prediction. 9.5 is 10 is perfect, because we know the answer, the population mean is 10. 9 is close, 10 is perfect, 10.5 is still close, 9.5 is still close, 10 is perfect, that's the actual answer. 11 is still within our reason, that's just 1 unit away. 11.5, that's too big. 10 is a perfect representation, 10.5 is really close. 11.5 is too far away, and 12. So if you count this, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sample means that gave really good estimates of what the population mean was. So in this example right here, it was basically 10 out of 16 represents the number of times that the sample, if you went through and just randomly made a sample of size 2, 10 out of 16 times you get a good representative sample that actually told you the correct answer, or really close to the correct answer for the population mean. Alright, so to find a percentage, just write in 10 divided by 16. So 62.625, which basically is the same thing as saying 62.5% of the time if you had a population of size 4 and a sample of size 2, we'd have an accurate representative sample 62.5% of the time, and the other samples would be not as good. These are too far away to be considered a good representative sample. So that failed, that failed. So you can see you had a couple failures, but more successes than failures. Right, the next thing it says, what is the mean the mean of the mean? Now that's kind of mean and standard deviation of the sample means of size 2. So we can do this a couple ways. We do this by hand, but what I'd probably recommend is we let our calculator help us calculate these really quick. So what they're asking us to do is to use those sample means and actually find the mean of the means. I know that's kind of like a second level, like almost like the movie Inception or something. So if you go to Stat Edit, I'm just going to take these in really quick, and then go up to L1 and hit Clear Down, go up to L2 and hit Clear Down or Clear Enter, either one. I'm going to clear out L3 too, Clear Down, and then go back to L1 and I'll start typing these in. So 8 was the first sample mean, 8.5 was the next sample mean, 9.5, I'm just typing in all the sample means, 10, 8.5, 9, 10, 10.5, 9.5, 10, 11, 11.5, 10, 10.5, 11.5, and 12. So I just put in all the data points, and now the easy way to have a calculator help us calculate the things we want is go in one variable statistics. So I hit Stat, Calc, one variable statistics, and hit Enter twice. And so the mean of the sample means is 10. So this is usually listed as mu sub x bar. So we just determined that mu, which is, it's kind of like a u with a line on the end of it, almost like a p. So it's not a script m, it's a u with a tail. So mu of x bar, that means the mean of the sample means. It's kind of ridiculous that we had means and then we did the means of the means, is equal to 10. Interestingly enough, it turns out that that's actually also equal to mu, which is the population mean. You remember we cheated earlier and we found the population mean, and we knew the population mean was 10. So the mean of the sample means is the same as the mean of the population. It's just another level. And then ask us to find the standard deviation of the sample means. So in this case, we're going to go back to the calculator, and right here it's approximately 1.118. So it tells us how the distribution, how the spread is of the sample means. And now this is another important part of the central limit theorem. It basically says you can do a proof of this in maybe a stat class, but the standard deviation of the sample means actually has a formula that you could say it's equal to the standard deviation of the population divided by square root of n, which is the size of the sample. Well, we never calculated the standard deviation, so let's go do that really quick. I think it's small enough we can do this one by hand even. You go back up to the top and calculate the standard deviation of the sample. Kind of see if we can review how to do this by hand. So if you remember, basically it takes a couple columns. So we start out with the data, which is usually x, and we have 8, 9, 10, 11, and 12. And then we want the mean, which actually I should write mu in this case, and which is 10. We already know the population is 10 for each of these, and then we find the deviation, which is basically x minus mu. So 8 minus 10, that's negative 2. 9 minus 10, that's negative 1. 11 minus 10, that's 1. 12 minus 10, that's 2. And then you square that, so the deviations are squared next. So that would be 4, 1, 1, and 4. And with the average of the deviations, that would represent variation. So if you add these together, 4 plus 1 is 5, 5 plus 1 is 6, and 6 plus 4 is 10. So we're going to do 10 divided by 4. And so the measure of variation would be 2.5. And then we take basically the square root of 2.5. You could have also done this with your calculator, just reviewing how to find standard deviation, which we did in the previous section. So if we take the square root of 2.5, we get a population standard deviation of 1.58, because the next step after you find the variation is to take the square root of that. So the standard deviation of the population is the square root of 2.5, which we're saying is approximately 1.581. Right, now the reason I did this is I wanted to help you see that there's a shortcut. Rather than find the mean of all the sample means and find the standard deviation of all the sample means, which would be really near impossible as this population grows in size. We could do it with this one because it was just so small, is the central limit theorem provided us with a formula. And it's saying that the standard deviation of the sample means should be equal to the standard deviation of the population, which we're going to say is 1.5811, over the square root of n. And remember, our sample size up here, we chose samples of size 2, should be equal to approximately 1.118. Let's see if it is. Alright, so if I just hit divided by the square root of 2, perfect, 1.118. So it gives us sort of a formula. Alright, now just to show you how complicated this can get really fast, I again started with the population of 8, 9, 11, and 12, and I wrote down every single possible sample of size 3. And look at that, just for every size sample 3, there's actually 64 samples of size 3. And I wrote down all the means of those samples too for you, because I figured that'd be too tedious to do on your own. I went ahead and did it for you. So I'll stop here and we'll actually look at this data in the next video.